Okay, the first concept I want to talk about is gradient. Gradient 刚刚讲是梯度，所以梯度是什么？在空间里头，你可以画出一个function 的等位面，叫做 equipotential surface. On this equipotential surface, basically this scalar function has the same value. Okay, just set say v equal to a constant, and then you have some constant value on the surface. But the value on the surface is different from the surface on the surface by a small amount, dv. Okay, and the surface normal direction is defined to be along an direction. Okay. Now, suppose you want to calculate the differential length. Calculate v with respect to some arbitrary length dl. Okay. 你知道这是 v 有一个值，这里 v 有一个值，所以呢，你如果 v 改变一点点 along this dl direction, then you can do this calculation. Right? dv over dl tells you the change of the potential. This v function with respect to the length along this length direction. This length direction could be along this direction, could be another direction. Okay. But using this chain rule, you can calculate dv over dn first along the surface normal direction first, and then do a differentiation of the dn over dl. N is along the surface normal direction. 在它的这个面的垂直方向上头，比如说，如果有两个面，我 dl could be along this direction, and then for any surface you have a surface normal direction. That is dn. Okay, and this is v1. This is v2. Equal to v1 plus dv. Okay. A little bit change of the value of v, and then you do a differentiation of dv with respect to dl, and then you can decompose this calculation into two steps. Number one, you first calculate the change of v along the surface normal direction, and then do the differentiation of this length with respect to this length. So if you construct a triangle, then this dn, because this is the perpendicular to the surface normal direction, so the length of this is definitely shorter than the length of this. Right? 因为它是垂直过来的，是最短的距离。这一段呢走出去了，所以这一段的距离比较长。那这里呢有一个角度 theta. Okay, so this dn over dl basically is equal to cosine alpha. Let's see, to be consistent, I should change this to alpha. So dn over dl is cosine alpha. Basically, this normal along the direction of the surface normal, any length like dl is a projection. The projection of this dl onto this surface normal direction is cosine alpha. All right. Well, any projection of this dl along this surface normal direction is dn. 你如果把它投影到这上头来的话呢，你就得到这个 dn 的这个长度。OK， 所以你在这里呢，你可以把这个这叫做 directional derivative， 把它写成 dv over dn and then multiply with cosine alpha. Okay, and now you define this dv over dn as a magnitude of gradient of v. 这个 symbol, very often we call it del. Okay, but when you write it into del v, we say this is a gradient of v. So if you do a directional derivative, dv along some length, direction. That is equal to the gradient of v dot product with the unit vector along this L direction. Because this dot product is going to give you this cosine, the projection cosine. OK， 所以呢，你在这个计算里头呢，在这做这个 directional derivative 里头呢，你的 gradient 永远都大于你的这个directional derivative， 因为这个 cosine alpha 的关系。So this has to be larger than this one. Okay, so this is the throughout this relationship, you understand that the gradient basically allow you to calculate the maximum change of some scalar function in space. 你算出来这 gradient of something means that you are calculating the maximum change of this scalar function v. And there's a direction associated with it. That direction is along the surface normal direction. Don't forget that a vector has two things. One is the magnitude, one is the direction. And gradient of some scalar is a vector. 它是一个向量, all right? Containing two important concepts. One is the magnitude and one is the direction. And the magnitude basically is the maximum change of this scalar function in space. The direction is along the surface normal direction of the equipotential surface of this scalar function. Okay, 所以这两个印象，这两个概念要很清楚。So I spell out the physical meaning of this. Well, I'm not teaching you mathematics. 我不教你数学的。OK， 我只教你物理的观念。数学的这个计算等等的话呢，我们台湾学生做的很多。但是呢，don't forget that you are in the engineering school， 或者在理学院学的是工程或者是物理。So what you want to learn is physics or engineering, and mathematics is going to be given to you for some detailed. You have to work out the details of the mathematics. But I'm not going to teach you mathematics, okay? So the important thing is that the gradient I want to summarize for you is the maximum rate of change of the scalar in space. Okay, 它是一个 scalar 在这个空间里头最大的这个改变量。然后呢，这个改变量有一个方向 the direction along the maximum change. Okay, so basically this direction is the surface normal direction of the scalar function. So don't forget this physical meaning, OK? 所以你算这 gradient 的时候，基本上你要算这个 scalar function 在空间里头改变的最大的最快的这个量是多少？那这个是有方向性的。Therefore, gradient is a vector, OK? Okay, then mathematics. I just summarized the formula for you, and this belongs to the effort of a mathematician. So I'm not going to prove this for you, all right? So a gradient can be written into this form. Basically, it's a partial derivative of some scalar function along some direction, x direction, y direction, z direction, and so on. And if you organize it into some general form with the matrix coefficient, then it looks like this, okay? And very often that we work with the x, y, z coordinate system. Therefore, the gradient, the form of the gradient in x, y, z coordinate system is quite simple. Basically, you do partial derivative of v with respect to x direction, and then give it a direction of x, and then plus the partial derivative of v with respect to y, and give a direction along y direction. And then again do partial derivative of v with respect to z, and give a direction in the z direction. And this mathematical form is going to allow you to calculate the maximum rate of change of v in space, and the direction is along the maximum change direction. Okay. 所以我要你清楚的就是当你做这个计算的时候，你脑袋里头想到了它的物理上你在算什么东西。That's more important than memorizing some mathematical formulas. Okay, any question? No? The next important concept is divergence. Well, let me flip back a little bit. When I do this calculation, I'm talking about the change of the value at one point. Okay, so this is something related to a single point only. But if we go back to the last page, those integrations are dealing with some physical quantities over some area, some length, some large microscopic 这个巨观的这个 dimensions. So remember that we are talking about point functions now. Even with this divergence of vector field, that is something to do with a point in space. OK， 在空间里头的某一点。那电磁学呢，它电磁理论必须符合一些这个在某一点上必须符合某些这个特性，那都是用这些 vector calculus 来这个 point function 来描述。OK， so the definition of divergence is that if you go to a point and then assume that there's a very, very small point with a very, very small volume, and then you do a cross-surface integration for this vector, that is a flux, right? If you integrate a vector along some surface, then this is a flux. And allow this volume to shrink to almost a point. And then this value is going to give you the definition of divergence of this vector. 所以这个 divergence 基本上要告诉你，就是在空间里头某一点上头，它的our flux of this vector per unit volume at a point in space. 在这一点上头，你做一个这个 flux 的这个积分，然后除以它的这个 volume， 然后呢，你就得到一个这个在这点上头平均的一个 flux. Okay, so let me say again, a scalar. This divergence of vector field is a scalar because you're calculating flux. Flux is the dot product. This dot product is going to give you a scalar. Okay, gradient is a vector, but divergence is a scalar, right? Because you are calculating the flux. The definition of this divergence is a net outward flux. Okay, because the surface is always pointing outward. So this is the outward flux of A per unit volume at one point in space. 所以你如果这个从物理上看这个图的话，你可以算出一个 flux, right? Because all the dot product A is along. Okay, for this configuration, this A is with some value. Let's call it A naught, and this is along R direction. This ds is with some value, but this as, the outward direction of this as, if I pick up some small surface here, this ds is also along some AR direction. Okay, no matter the surface you pick here or here or here or here, it's always along R direction. If you construct a spherical surface, 一个圆的这个面 Therefore, you will expect that this flux calculation give you positive value all the time. So this A that was ds is going to be something that is A not ds. And then this is a positive value. So you always get something. So this is, if you calculate the divergence of A at this point, then you get something. All right? But look at this field called solenoid field. If you calculate the divergence of A at any point in space, say you pick up a point right here and then construct a surface. For this surface, you have a dot product that is a dot product that gives you this is the ds surface direction, and this is A. For this two dot product, you get something positive. But for the dot product right here, your surface is here, but the definition of the surface direction is along the outward direction. So now you have a surface direction along this direction in the backward direction. So the dot product of this and this is going to be a value, a negative value. That will exactly cancel the integration here from the surface. So for this solenoid field, the divergence of A is equal to 0. Okay, because the surface direction flip in the backward if you deal with the surface. But the direction of the A is still along this direction. OK， 所以这里积分出来 A 大 ds 积分出来的量跟 A 大 ds 这里积分出来的量刚好相等，但是差一个负号，所以你积分加起来的结果呢会是0。所以 for this kind of solenoid field, the divergence of A has to be equal to 0. OK, but for this this kind of field with a source at the center, if you pick up a divergence of A somewhere from this field, from this point, then you get something. 所以这是告诉你说，当你算这个 divergence 的时候呢，你如果有一个面，它的 net flux 是存不存在？存在的话，它有多大 ？OK， 等于是它是算这个 source 有多强 ？OK， 那 so the divergence theorem, while once you have the point function, you need to deal with macroscopic phenomena, the macroscopic physics. Then you have to convert, do an integration to convert this point function to some macroscopic function. So there's a divergence theorem tells you that if you move this theta v to this side and do integration over the volume, divergence of A over the volume, that is equal to the surface integration of A. And this is called divergence theorem. Okay, 这个结果呢 you can in fact sort of conceptually infer from this relationship. Okay, you just move this volume to the left hand side and then allow this volume to be big. Then you have sort of this relationship. But a mathematician is going to tell you that this is not enough to prove a theorem. You have to go through a lot more rigorous way to prove this relationship. And I will just point out a little bit to you, but not give you all the details, because you can find the details in your textbook. 你如果有一个大的这个 volume, okay, and for this calculation, basically, if you take a divergence of A everywhere in this volume and take a integration over this volume, you end up having the flux calculated on the surface. 所以物理上告诉你说，你如果在这里头呢做这么一个 volume integration 的话，其实它是相当于就在这个表面上头做 surface integration. OK， 这是物理上它的意思。How do you prove it? Well, you can always decompose a big volume into small ones. OK， 这个小小的一块一块。这个 volume integration 在这个边界上头呢，因为它的这个你把这个每一块都用这个来计算 ，because I'm reducing this volume to a small differential volume, so this equation is valid at this point, for example. Okay, and then you do an integration, for this small volume, and you find that at the boundary, the surface for this volume, the surface normal direction is along this direction, right? Outward direction. But for this boundary, for this volume, the surface normal direction is along the opposite direction. 所以呢，你在这个 surface 的这个 interface 的 integration 呢，全部都会相消掉，都会抵消掉。对这个 surface integration 来讲，这个边界只要是有边界的地方都会抵消掉。所以到最后呢 ，finally you only have to deal with the surface integration on this big volume。这个里头的小的这个 surface integration 全部都可以拿掉 ，because of this at the interface when you do the surface integration for this volume you have a surface vector going down, and for this volume you have a surface normal direction that going up, and the integration on the surface is on the interface will be just cancel or just cancel each other, okay, and then finally you end up having a surface integration over the whole volume， 只剩下这个外围的这种 cross surface integration 而已，里头的这个小的这个面积全部都不需要考虑。Okay, so this is the way to prove rigorously for this divergence theorem, and you can look up your textbook to find all the details, but basic concept is like this. Okay, so you have a divergence of a vector and integrate over for the whole volume, then you end up having a calculation of the total flux associated with this volume. Okay. 我刚刚特别介绍到 if you have this kind of solenoid field, the divergence of A is equal to 0. So from here on, if you calculate the divergence of a vector that is equal to 0, then we say that this A is solenoidal. OK， 它的场的样子呢，就会类似这种样子。这个场进到一个面，它又从另外一面出去了，不像这个哈，它场呢一直都是往外的方向或朝某一个面的方向走。但是呢 ，for this kind of solenoidal field, if you construct a surface, however, outward flux is going to be cancelled with the inward flux, and this is called solenoidal. Okay. And basically, the magnetic field is sort of similar to this kind of field patterns. Okay, so now mathematics. You can derive the form of divergence of A given by this general expression, and those H1, 2, 3 are matrix coefficients. Okay. 所以呢，之前已经跟你讲这个 H1, H2, H3 是什么东西？U1, U2, U3 are different for different coordinate system, and the simplest coordinate system you are familiar with is the rectangular coordinate system. That is x, y, z coordinate system. Okay, so in this x, y, z coordinate system, the divergence of A has a very simple form. Basically, you need to remember that the divergence of a vector is a scalar, alright? 所以这里已经没有向量了。Basically, it's a component of A, component of x of A. You take a partial derivative of it with respect to x, and then sum with the component of y of A, with partial derivative of it with the y. And then partial derivative of AZ with respect to Z, and sum them over to give you a scalar. Okay. So now, if I want to summarize a little bit, basically when you do divergence, you are calculating the flux at one point per unit volume. That's it. Okay. This is a very simple summation, and very often that you have to do this divergence theorem when you calculate problems in electromagnetics. And this is divergence theorem is sort of converting the concept of a point into a macroscopic surface or macroscopic volume. 因为我们人的世界里头呢，经常应用上头的话是巨观的，不是只有空间里头一点。Okay, so this theorem basically is give you the chance to convert the concept of a point into a macroscopic area of volume. Okay, and a question? 所以我们介绍了这个 gradient 跟 divergence. Okay, So last time I told you there's another important concept, that is circulation. That is a calculation associated with the rotating ability of the rotation vector. Okay, so now let's look at the definition of curl of a vector field. 没有学过 vector calculus 的请举手。你一定不是电机系或物理系的。交换生。大几？
严格来讲是
大二。你没有学过工程数学？
没有，就没有学过 vector calculus。
没有学过 vector calculus。你原来是什么系？
我原来是因为我是交换生，所以我原来在那边是读电子工程。
电子工程系，电子工程系，学校里头也有电磁学的课，有没有？但是工程数学里头没有上过 vector calculus。
因为整个 curriculum 是不同的嘛，我们因为工程数学我们就分开几部分的数学来讲，因为我就是没上 vector calculus。OK。
在清华大学电机系，这个我们是告诉老师说，上电磁学的时候，这个部分不需要上。因为这个部分 vector calculus 是在工程数学里头有特别 emphasize， 有特别的强调。那所以电机系后来把这个电磁学2把它变成不是必修课，就是希望电磁学现在的这个电磁学1变成电磁学之后呢，要教的越多越好。所以呢，建议老师不需要帮你们上这个 vector calculus， 所以我们还是花一点时间帮你 review 一下。所以你如果没有修过这个 vector calculus 或者是不熟悉的话，你要自己花点力气跟时间去读一下这个D.K. Chen 这本书的第2章。OK， you have to pick it up by yourself. Okay, the curl of a vector field is defined to be this expression. When you look at this expression, now you sort of feel that this is a calculation of the circulation, right? Because this is a cross-path integration of some vector along some path. But this is a cross-path integration. Okay, some cross-path integration. And then you have some vector of A, and then allow this path to shrink to a point in space. So you allow the surface of this delta S approach 0. There's a surface associated with it. Okay, so you calculate some circulation and average it over a small point surface. But be careful. There's a vector. There's a direction associated with it. There's a direction associated with it because in space, at the point, you can construct the path arbitrary. All right, you can do your surface like this. Okay, you can in space. You pick up one point, and then you have some surface like this. But you can also pick up a different surface, say this surface. At this point, this point does not move, but this surface can change all the time. So when you calculate the circulation nearby, right at a point, you have to tell people what kind of surface you choose. Otherwise, you don't get a single value. If you pick up this surface, then you can calculate some circulation. If you pick up this surface at the same point, you can get different value. So we have to define this curl of A for some particular path that gives you something meaningful. Okay, so the definition is that you go to a point and then try to select the surface such that this calculation gives you a maximum value. Because maximum value is unique. 最大值只有一个， 所以呢，你就挑到那一点之后呢，让这个面转，选到你得到最大值之后呢，这个面就固定下来了。And then this surface has one direction， 有一个方向。Okay. So basically, when you do this circulation and divide it by the small differential surface, you have to choose the surface direction so that you get maximum net circulation for this calculation. Okay. So for this curl of A is a vector, and the curl of this vector A is the maximum net circulation of A per unit area at some point in space. Okay, and the direction, because this is a vector, then there's a direction. The direction of curl of A is chosen to be the surface normal direction of this small area, delta S, with which you get the maximum value of this circulation calculation. Okay, whenever you deal with gradient, divergence, curl, always bear in mind the physical picture. OK， 这个在亚洲台湾或者台湾的这个教育里头，我们 overemphasize 这些数学的计算。昨天你们电机系有个学长，以前是我的导生，他到这个Stanford 念书，我把他推荐进去之后，这个昨天他回来给你们有一个演讲，有没有？陈宏宇。OK， 那他回来之后就完全了解为什么我在上课的时候一直在强调这个物理的概念，这个 physical picture，physical sense， 而不在这个数学的这个计算上头。因为他回来之后，他昨天就跟我讲，的确这个到 Stanford 上课的话，这个电机系里头老师的上课方式或强调了，就是这些他们有非常强的 physical sense 跟 physical 的 picture 在这个里头。然后呢 ，from which you can have invention。然后呢，这个对工程或者物理的人来讲的话，你可以把这个数学的部分交给数学家来帮你解。OK， 重点就在于你的这个 physical sense 或 physical picture 有多强。从那个上头，你可以有一些重要的发明或发现出来。OK， so whenever you do this vector calculus calculation, you have to bear in mind the physical picture associated with it. OK， 那现在年轻人都非常的 aggressive， 也就是相当的这个积极，很冲劲，很强。那你们这个对你们人生规划，追求卓越的话，都有很强的冲劲，所以经常同学们在某个时间点的时候呢，要推荐甄试，或者是要申请国外的学校，经常会来找老师们写推荐函，但是你注意到有效的推荐函、有效的推荐，通常是里头，这个信里头要言之有物，也就是要把故事写出来，而不是用一些形容词说你 outstanding excellence without any story. That kind of reference later is not going to be useful. OK， 所以很有趣，就是几年前我到北大去给一个演讲，然后呢就有一个学生演讲之后过来跟我聊了一下，但是大概3-4年过去了，前2天他就送一个 email 来，叫我推荐他到 Stanford 读书。我说这个没有这个言之无物的推荐函，其实对学生申请或推荐的话，其实是负面的。所以你如果有些规划将来你要这个达到什么目标，需要老师们帮忙或之类的话，你上课的时候的表现，你的跟我的互动，跟老师的互动，或者是这个学习的一些互动表现呢，就是要随时呈现出来，不是到了要申请学校的时候呢，这个突然之间送个 email 来，嘿，我要进入全世界最好的学校，请推荐我。我说我跟你讲过3句话，那样子推荐函一出去的话，人家会觉得你是没有 common sense。OK， 说这个学习跟互动是很重要，尤其是对于你将来下一步如果需要人家帮你 描述你这个人的话呢，别人才有办法言之有物。Okay, so this is the definition of curl of a vector. Basically, you are calculating the maximum net circulation. Don't forget this keyword, maximum. Okay, because this maximum, it makes this calculation unique, a single value. Associated with this, you can find a Stokes theorem that allow you to convert the surface integration of curl of A into a cross-path integration. And you should compare this expression to the divergence theorem. The divergence theorem is converting the divergence of a vector, the volume integration of a divergence of vector into a surface integration. Okay, but now the Stokes theorem convert the surface integration of a curl of a vector into a cross-path integration. While intuitively, if you just put this delta s to this side, you sort of construct this relationship. But again, the mathematician will tell you that this is not going to be rigorous enough to prove this Stokes theorem. So the way to prove this relationship is that, again, you decompose. Now, consider this is not a volume, it's a surface. You decompose this surface into small areas. Okay? And for the boundary, you do this surface integration. But on the right-hand side, you do a lot of cross-path integration. Okay, you do a lot of cross-path integration, and just look at this boundary. Let me construct another boundary right here. Okay, think about this circulation calculation and this circulation calculation. At this boundary for this circle, say you have a dl length along this direction. Well, you have to follow the right-hand rule. Okay, so suppose that your vector is along this direction and your dl is going like this. So I have a dl going like this. But for this small surface, if you apply right-hand rule again, then your dl is going to go like this. And then you look at this vector and this vector. They are going in opposite directions. So at the junction of these two areas, the circulation integration will cancel each other because one path is going this direction, the other path is going this direction, just in the opposite direction. So you don't have to calculate the value associated with any interface. Okay, the net result is that you only have to deal with circulation calculation at the boundary. Any interface will just cancel each other. 这就是你如何证明这个 Stokes theorem 的方法，意思跟之前的这个 Divergence theorem 的证明是一样的。你把它分成一小块，这时候呢，这个就可以拿来用。那在这个边界的地方呢，因为你的方向是刚好相反，所以方向在这个边界上的积分呢，会互相的抵消掉。Okay, therefore, the surface integration of curl of A across the whole surface will be just equal to the cross-path integration of A along this boundary, and you don't have to deal with any interface integrations. Okay, and this is the Stokes theorem, and this is the way how you prove it. Okay, 有没有问题？我想这个每个式子、每个物理观念我都交代得很清楚。Okay, I hope that you can pick it up. Well, now now that you know that curl of A is calculating circulation, basically you are calculating the ability of this vector circulating at some point. So this is a concept quite different from the flux. Flux is calculating the ability of this vector expanding along some direction, okay, from a point source. But for this curl, you are calculating the ability of this vector circulating about one point, okay? So if you have this curl of A equal to 0, this means that this A does not rotate. This vector does not rotate. And so if you in space, if you calculate curl of A equal to 0, it means that this vector is irrotational. It does not rotate. Okay, so this makes sense to you. 我以前跟以前电机系不少学生讲说我以前在美国受教育的时候呢，老师们最喜欢的一个口头禅就是Does it make sense to you？ 这个物理的概念比这个数学的 detail 还要重要的多。Okay, but in our training a long time ago, we spent too much time in mathematical derivation. Okay, now you have to pick up the physics. Well, this is the mathematics. So I just show you the form, and then you can always check the table or some mathematic textbook to find out the form with the matrix coefficient. And again, very often we use rectangular coordinate system. Then for the rectangular coordinate system, curl of A is expressed like this. You can use the matrix to calculate it. Okay, so just put it here for your reference. 所以我们介绍了3个重要概念 ：gradient, divergence, and curl。好，这3个呢，经常混在一块来计算一个物理量。OK， 在电磁学里头用到的很经常用到的一个计算呢是 gradient of something, and then you take divergence of it. Okay, and this is the maximum rate of change of a scalar function in some space, and then now you calculate the flux per unit volume associated with it. And this is called Laplacian operator. 这个 del 的 square 是 defined to be divergence of gradient of v, and it's a scalar. Okay, this is not a vector. Gradient of v is a vector, but when you take a divergence, you will be calculating the flux, and then you have a scalar. And in xyz coordinate system, this expression is this. Well, how do you get this? Basically, you go back to the gradient. Okay, you go back to the gradient and you have a vector like this. And then for the divergence, you want to take this, the partial derivative of this with respect to x again. Right? For divergence, you have for divergence of A, you have ax derivative with respect to x, ay with respect to y, plus az with respect to z. 这是你的 ax, ay, az. So you do one more derivative to get Laplacian of v is equal to this. Okay, so simple enough. 这个形式很简单，但是呢，在电磁学的解里头，很多都是直接从这里开始。Okay, well, this is the scalar Laplacian, but in fact, there's a definition for vector Laplacian. Okay, for the vector Laplacian, the definition is a little bit complicated. That is the gradient of divergence of A. 你注意到这个 gradient give you a vector. This will give you a scalar. So the whole thing is a vector. So vector Laplacian is a vector. Okay, vector Laplacian is a vector. Then you have to do double curl for a vector. The subtraction of this from this gives you a vector Laplacian. Well, there's reason to do this definition because when you deal with time-varying field, very often you have to do this calculation. And for in the xyz coordinate system, the vector Laplacian is quite simple. Okay, it's a scalar Laplacian of ax multiplied with the direction of ax plus the scalar Laplacian of ay multiplied with a unit vector along y and plus the same thing along z direction. OK， 所以对于这个 A 来讲的话 ，the first term ax basically is you can expand it for the first components. And then you can expand the second component and then the third component. Okay. And 这个是你的 scalar Laplacian. But for vector Laplacian, you have to calculate the three directions: x direction, y direction, and z direction. Okay. So go back to sort of review what I told you. And last night, you should already receive the homework assignment number 2. And it's due on next Wednesday. 下礼拜三有第二个作业要交。然后呢，题目还有点多，所以你早点开始做 ，OK。然后下礼拜一我们有一个这个期中考，那范围呢会是到下礼拜三交完的范围，就是期中考的范围。OK。